Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will learn how to design artificial lift, which is electrical submersible pump, and how to create nodal analysis from a well equipped with ESP. All right, but first we will model a well that is unable to flow and hence need ESP to make it able to flow. All right, we will first set up the well. We are now inside the WellFlo and we will perform the simulation using WellFlo. We are now inside WellFlo, configuration, model navigator, initialization, general data. You can type in general data here as per your requirement. Go forward. Well and flow type. First, we select producer, no artificial lift, flow type tubing, fluid type black oil, well orientation vertical. All right, and then forward flow correlations, we select Dance and rows with well and riser L vector of 1. Forward reference depth, well type onshore, and 0 depth at wellhead. Forward. Now we go to fluid parameters. You can follow me. The oil specific gravity 0.85 and the API gravity will be calculated. Gas specific gravity 0.65, water salinity 30,000, ppm, and water gravity will be calculated. All right, bubble point, solution GOR, and oil formation volume factor will use Glasso equation, oil viscosity Buell et al., gas viscosity Carr et al., and surface tension we will use basic. No inorganics. And for this section, PVT data calculator, if you want to create the results, pressure at 3072, temperature at 200 degrees Fahrenheit, and produced GOR 500, standard cubic feet per stock tank barrel. You can press calculate to obtain this information. All right, apply, and then we go to reservoir section. We will create the IPR using analytical model. So we call it reservoir. All right, reservoir, and pressure at 3072 PSIA and temperature of 200 degrees Fahrenheit. Middle of perforation 8,500 feet with permeability of 79, thickness 58 feet, and Wellbore radius of 0.35 feet, water cut in fraction 0.6, and gas oil ratio of 500 standard cubic feet per stock tank barrel. Okay, and we will use Vogel. We will use Vogel equation and total Darcy skin 1 for the skin options. And we go to drainage area. All right, and circular for drainage shape. This one, or drainage area, or maybe drainage area will be calculated. Equivalent drainage radius of 1000 feet. Drainage area will be calculated. DHC factor, this one. So we assume a circular reservoir. So as you can see, the productivity index is 5.83 with absolute open flow of this one, more than 10,000 stock tank barrel per day with total Darcy skin of 1. All right. This is the IPR. Okay. Rel perm, relative permeability, we can leave it as default. All right. Okay, and then we apply and we go to Wellbore section. First deviation, we will create a vertical well. Data type MD TVD angle, enter data for MD and TVD. So we will input MD measured depth and TVD through vertical depth. Because this is a vertical well, so the measured depth will be equal with the true vertical depth of 8,500 feet. Update plot. All right, this is the plot, purely vertical well. We press apply, and then we go to forward. We have two tubings. We call it tubing 1, starting from 0 down to 3,000 with external diameter of 5.5, internal diameter of 4.892 with default roughness. Okay, and then for the second tubing, we call it tubing 2, starting from 3,000 down to 8,000. All right, and then the internal diameter of 4.5, internal diameter 996. Right, so for the external diameter is 4.5 inch, and then internal diameter of 3.996 inches. Okay, with default roughness. We press apply, and then we go to casing. We can make 3 casings. We call it casing 1, starting from 0 down to 3,000 with external diameter of 9.513 with internal diameter of 8.681, and then second casing starting from 3,000 down to 8,000. Okay, and this one is 6.954, 6.184, or we can modify it to be 7 inches with default roughness. And then the last casing, we call it casing 3, starting from 8,000 down to, of course, 8,500, 7 inches, and then the same internal diameter. Apply. All right, as you can see. Lastly, we will input the temperature model. Okay, we can use calculated for the model and surface surrounding temperature of 80 degrees Fahrenheit. And then this one, 8,500. 8,500 will be calculated. Okay. All right. Apply. Yeah, as you can see, we are ready. We have completed all the data input, so we can check at dashboard. This is our natural flow model. The wellbore data and reservoir data you can check, and also the fluid properties. Okay, so far so good. And now we can go to analysis to perform the nodal analysis. All right. As you can see now, nodal analysis mode, operating point. We want to find the operating point if the well can flow, of course. Stability check is checked. And the outlet node, the wellhead pressure, okay, 200 degrees or 200 psia. The bottom node, of course, at the reservoir. Solution node at casing 3 at bottom hole. Okay, and then we can set range. We can use auto range. Click OK. Apply. Calculate. All right, so as you can see, there is no operating point. So at the given condition for the reservoir condition, wellbore condition, and also fluid condition, you can see the well cannot flow. The well is dead. Maybe because of course, primarily, of course, because of low reservoir pressure. The reservoir pressure is unable to push the fluid to flow from the reservoir or from the bottom hole to the surface. Okay, maybe also because of the fluid is so heavy, because now we have fluid with water cut of 0.6 in fraction. So it means that majority the fluid is composed of water, and water is heavy. The gravity is bigger compared to oil and of course to gas. All right, so this combination, and also the wellhead pressure is 200. Maybe if we lower the wellhead pressure down to 100, calculate, yeah, you can see the well is able to flow. We can make it even smaller, 50 psia. The well can flow, obviously, all right? But at our given condition, operation condition, the wellhead pressure is 200 psi and the well cannot flow. And at this condition, of course, we need artificial lift to make the well able to flow again. And that's the second chapter of our video, which is to design and to install electrical submersible pump. All right.